Generative AI didn't suddenly appear out of thin air. Developing these systems required a decade-long engineering effort to overcome strict physical and mathematical limits. Before the massive models we use today, early natural language processing relied on classical sequential architectures. These were systems like recurrent neural networks, or RNNs. Early models used time-based recursive transmission, processing linearly. Calculating the next token required the preceding one. This bottleneck prevented GPU parallelization, utilizing just a single row. Finally, long sequences diluted information. Earliest nodes faded to black, causing the AI to forget. Early AI was trapped by linear time. To reach a global understanding of long texts, the industry needed to abandon these recursive structures for something entirely different. The turning point arrived in 2017 with the invention of the transformer architecture. The transformer introduced the self-attention mechanism, allowing every sequence token to calculate its relationship to all others at once. This mathematical shift perfectly matched GPU data processing. It enabled massive parallelization, giving rise to the scaling law and trillion-parameter models. But as these models scaled, they hit a second bottleneck. The sheer amount of computation required to run a dense model of that size created a physical power crisis. In a dense model, every single parameter activates for every single word generated. This causes massive spikes in memory bandwidth and power consumption that simply aren't sustainable at a global scale. Developers built mixture of experts architectures. A router activates only relevant pathways per token, leaving the rest dark. Additionally, attention compression projects massive memory requirements into tiny latent vectors, shrinking the physical data footprint by 4 times while retaining its core structure. These efficiency gains were the only way to keep AI growth on track. Without them, the energy requirements for a trillion-parameter model would have exceeded the capacity of modern data centers. By 2025, with hardware efficiency stabilized, the industry encountered a third bottleneck, the imitation ceiling. For years, AI was aligned using supervised fine-tuning, where human experts graded the AI's answers. But this process capped the AI's ability at the level of the humans writing the data. This training style encouraged models to memorize patterns and mimic human experts, rather than developing a genuine understanding of the underlying logic. To break through, the industry shifted to reinforcement learning. Models are now tested against rigid, rule-based verification, like a code compiler. If an output fails, the model reconfigures its approach and tries again, iterating continuously until it finds a solution that satisfies the objective requirements. This produced a sudden change in behavior. Models like DeepSeek R1 and OpenAI's O-series began to exhibit slow thinking traits, establishing multiple hypotheses, hitting dead ends, and self-correcting their work. Shifting to reinforcement learning changed how the software approaches a problem. The system moved from mimicking the patterns of its trainers to solving problems through a continuous process of internal verification. As we move into the 2026 era, models are outgrowing text. Earlier versions used a patchwork approach, trying to plug separate visual encoders into a text-based brain. The next step is native multimodality. In these architectures, images, audio, and text are all processed together in a single glowing core from the very start of training. By splicing all these inputs into a unified block, or token, the AI gains a native understanding of physical geometries and real-time audio. It isn't just reading about the world, it is beginning to understand its physical properties. But this new physical capability is colliding with a fractured geopolitical landscape and the limits of the hardware itself. The US strategy relies on massive cloud capital and specialized NVIDIA architectures to build closed-source ecosystems. In contrast, Chinese innovators are bypassing hardware sanctions by embedding highly optimized open-weight models directly into industrial robotics and autonomous vehicles. The last decade was about teaching AI to process data on a server. The next is about unleashing that intelligence into the physical world.